Combustion analysis is an analytical technique that you can use to identify the empirical formula of a hydrocarbon. Now, a hydrocarbon is a compound that's made up primarily of carbon and hydrogen, thus the name hydrocarbon. Also, hydrocarbons sometimes contain oxygen in their chemical formulas and also are frequently found with nitrogen in the chemical formula. So this combustion analysis technique can work for all of those compounds. So this video, I'm going to show you how to complete a combustion analysis problem. Now, in a combustion reaction, we have a hydrocarbon plus oxygen always yields CO2 and H2O. Now, we are making the assumption that it's a complete combustion. A complete combustion produces only CO2 and H2O. So we can take advantage of what we know. If you look at the generalized form of this chemical reaction, you can see that the coefficient for the carbon in the hydrocarbon is the same as, the subscript for the carbon in the hydrocarbon is the same as the coefficient for the carbon dioxide that's produced. Likewise, the coefficient for the water that's produced is also related to the subscript for the hydrogen. So taking advantage of these relationships, we can use the data about the mass of carbon dioxide and the mass of water produced to work backwards to figure out the chemical formula of the hydrocarbon itself. So let me show you how this works. Here is a typical problem for a combustion analysis problem. So we have a hydrocarbon, polyethylene. It's a polymer, so it's a very large hydrocarbon. So we're going to find the empirical formula. And remember, the empirical formula represents the lowest whole number ratio. Now, this kind of the elements in the compound. This compound, polyethylene, is a polymer of just carbon and hydrogen. All right, so we learned from the problem that we do a combustion analysis. So we burn it with excess oxygen. And from the analysis, we get 0.00394 grams of carbon dioxide, and we get 0.00161 grams of water produced. So we're going to use that data to figure out the chemical formula. So here are the steps. The first thing we're going to do is we're going to use the mass of the carbon dioxide to find out how many moles of carbon were in the compound. Then we're going to do the same thing with the water. We're going to use the mass of water to figure out the moles of hydrogen. Once we know the moles of carbon and the moles of hydrogen, we're going to use those two numbers to find the lowest whole number ratio of carbon to hydrogen in the chemical formula, and that will be the empirical formula. All right, so let's try it. So here's our first step. So we know the mass of the carbon dioxide produced from the combustion reaction. So if we use that mass, we're going to divide by the molar mass of carbon dioxide, which is 44.01 grams per mole. And the third step is very important here. The next step is that for every 1 mole of carbon atoms, we have 1 mole of carbon dioxide. It's a 1-to-1 ratio. So if we do that calculation, we can calculate the moles of carbon. The next thing we're going to do is we're going to find the moles of hydrogen. Now, in this case, we need to start with the mass of the water, and we're going to divide that by the molar mass of water, 18.02. Then we're going to use the mole ratio. Now there's 2 hydrogen atoms in every 1 water molecule. So we have to multiply the number of moles of water by 2 to get the number of moles of hydrogen in the compound. So once we do that calculation, you can see we have moles of carbon and moles of hydrogen. So the last thing we need to do is figure out the whole number ratio. So the easiest way to do that is to divide the larger number by the smaller number. In this case, hydrogen is the larger number of moles. So we take the moles of hydrogen divided by the moles of carbon, and we get 1.99598. Well, 1.99 is close enough to 2 for an empirical formula calculation that we're going to round that up to 2. So it's a 2-to-1 mole ratio. So for every 2 moles of hydrogen, we have 1 mole of carbon. So we can translate that into our empirical formula of CH2. So some things to note here is that hydrocarbons, the hydrogen is usually larger. The subscript for hydrogen is usually at least twice that of carbon. So in these kinds of whole number ratio things, you're usually going to have hydrogen is the larger number of moles divided by carbon. Now, what about a more challenging problem? Okay, sometimes, as I said at the beginning, sometimes we have nitrogen and sometimes we have oxygen. So here's a typical problem that would involve another step. So in this question, we have an unknown compound that produces carbon dioxide, water, and nitrogen gas in the combustion analysis. So what we need to do is figure out the empirical formula of the compound. Well, it's obvious that this compound contains carbon and hydrogen and nitrogen. Okay, and it's burned in excess oxygen. So we're going to assume that oxygen is not in the chemical formula. All right, so this is going to be very similar to before, but except we have one more step. Because if you look here, I've written a generalized equation for our hydrocarbon that includes nitrogen. So now we're burning our compound in excess oxygen, and we're producing carbon dioxide and water as normal, but we're also going to produce nitrogen gas. And let's not forget that nitrogen is a diatomic element. So we have to work in the nitrogen to figure out the moles of nitrogen in the compound. And then we'll do a whole number ratio between the three elements. Okay, so here we go. We'll find the number of moles of carbon. So we start with the mass of carbon and divide by the molar mass of carbon. And there's a 1-to-1 ratio between the number of moles of carbon atoms and the moles of CO2. So that's our first step. Next, we're going to figure out from the mass of water how many moles of hydrogen were in the compound. So we started with 6.608 grams of water, divide by the molar mass of water, and it's a 2-to-1 ratio of hydrogen atoms to water molecules. So we have to multiply the number of moles of water by 2. So now we have moles of carbon. And here's our third step. Oops, that should just be N2. We know how much N2 is produced, so we're going to use that to figure out the number of moles of nitrogen atoms in the compound. All right, so we have the mass of the nitrogen, 2.057, divided by the mass of N2. This is where it gets a little confusing because nitrogen in the chemical equation is the element nitrogen, which is diatomic. And then there are 2 nitrogen atoms for every 1 nitrogen molecule. So we have to multiply the moles of nitrogen by 2. So I put that step in there as well. So now we have moles of carbon, moles of hydrogen, and moles of nitrogen. So we need to get the whole number ratio between those 3 elements to figure out the empirical formula in the compound. Well, if you look at the 3 numbers, our lowest number is nitrogen. So we're going to divide all 3 of those number of moles by the number of moles of nitrogen, since that's the smallest of the 3. Okay, so I started off by taking the moles of, let's see, what was that? Moles of carbon first, divided by the number of moles of nitrogen, that gives us 2. Moles of hydrogen divided by moles of nitrogen, that gives us 4.99, which is 5. And, well, nitrogen divided by itself is 1. So we have a 2 to 5 to 1 mole ratio of carbon to hydrogen to nitrogen. So that translates to an empirical formula of C2H5N. So here's our combustion analysis. So again, we're using what we know about the combustion reaction, and we're also using what we know about stoichiometry to work backwards from the products to the empirical formula of the hydrocarbon.